All right, this is Unit 5, Section 5.6, continuing our idea on binomial random variables, Day 2. And so again, as we look at our schedule here, we're at binomials Day 2. We'll finish with geometric and then review and test after that. All right, so looking at what we did last time, we were looking at this binomial setting with bins. And so we needed to meet the binomial setting, we needed it to be binary, so success versus failure, independent, knowing one outcome doesn't influence the next, a set number of trials, and a set probability for success. Meaning we really need these two criteria in order to make this binomial setting. We learned about a formula last time, but our calculator is programmed to do this as well. And so I'm going to walk us through an example using our roulette wheel again and looking at the probability calculator. And so in our example, it says in roulette, 18 of the 38 spaces on the wheel are black. Suppose you observe the next 10 spins of the roulette wheel. What is the probability that exactly 4 of the spins land on black? All right, so we want to think about this. It's asking us a probability question. It has not told us it's approximately normal, so we can't use our normal pieces. And we're not looking at just one outcome. We're looking at 4 outcomes. And so when we look at this, it is binary. You either get a black or you don't. It's independent. One spin shouldn't be influencing the next. Otherwise, our casinos are really ripping us off. We're going to have a set number in here. So I'm going to say my set in trials is 10. We have a set probability of landing on black. That's our success. And we're looking for 4 trials that are exactly 4 of them to be black. And so when we look for this probability of exactly 4, we can actually do this on our calculator using the binomial PDF. So just like when we see normal and we go, woohoo! When we can recognize these two pieces, we can go binomial. And so we're going to put that in our calculator. We have in trials. We have P, 18 over 34. Oh, I'm sorry, 38. And we're looking at 4 here. All right, so then in my calculator, I'm going to be able to do this using second vars for our distribution menu. I'm going to choose 0, which is our binomial PDF, and then enter these pieces here. Okay, I'm using PDF, not CDF. So PDF is going to be precisely, I think I misspelled that, but it's looking at exactly the number of outcomes. CDF we'll look at later, and it's looking at less than or equal to our successes. And so we might have to do some adjustments because, again, this is where Beyonce comes in again. All right, so looking at our calculator, I'm going to go to my distribution menu, so I need to hit second. I need to get my pen here. So I'm going to go second, good grief, distribution. I'm going to hit 0 because that's my binomial menu. That's F, so maybe it's not 0. Let's double check. Second, distribution. And I'm just going to scroll, so maybe it's further than what I thought. I thought it was at 0. Oh, it's at A. All right, so I'll back up to A and enter. All right, so I have 10 trials that I'm doing. I have a probability of success of 18 out of 38. And the value I want is exactly 4, which is why I'm using PDF. And enter. So instead of finding the binomial coefficient, all those combinations of 4 successes within those 10 different trials, now my calculator does that all in one step. And so we get this 22.5 here. So there's a 22.5% chance that we will get exactly 4 of the spins that will land on black. So the next one, okay, we're still using this information. It says, what is the probability that at least 8 of them, okay, land on black? All right, so this is where we would use the now CDF command on our calculator. Okay, CDF is going to be less than or equal to. So right away we have red flag going off here. And so our red flag is that our symbols don't match. So if I think about this, I have, that 1, 2, 3, 4, 5. I'm kind of going 7, 8, 9, 10. So I'm looking for 8 or more. That would be at least 8 of the spins land on black. Okay, so that's going to be the opposite of 7 or less. So what I'm going to do is I'm going to look at the probability of taking 1 minus the probability of my example being less than or equal to 7. This is the piece that our red flag fixes. Now I do have that symbol that I wanted to have here. So when I put this in my calculator, I'm going to do 1 minus, and now I have a binomial. This is going to be CDF, cumulative here, so that I add the 1, the 2, the 3, the 4, the 5, the 6, and the 7 all together. So I want it to be cumulative, not exactly. And then I put in my commands, 10, 18 out of 38, and now I have 7. Most frequently missed thing is not changing this from 7 to 8, from 8 to 7 and not subtracting. So we had to fix this. This is our question we're addressing, but if we want to use our calculator, we need to adjust for that. All right, so when we look at this, now we're going to get 1 minus, and I'll put this in my calculator. 1 minus, and now I have binomial. I'm just going to scroll up from the bottom to get CDF because I want a cumulative probability. We still have our 10 trials. We still have our probability of 18 out of 38. And we're looking for 7 or less. And so Beyonce's happy going to the left there. And when we get this, there is a 0.038 probability of at least 8 of the spins landing on black. So it's going to be really unlikely if you keep betting on black and black and black for those 10 spins that you would get 8 of them or more landing on black. So you want to mix it up that's not going to be very likely. All right, looking at another one. And so it says you can use the binomial setting with a simple random sample of size n from a population n as long as this criteria is met. So this is where if we have a simple random sample from a population. So this is because this idea of you're sampling more and more from the population, the probability of success changes too much to be considered constant, since there is a change in the remaining pool of the population, no longer closely resembles the original population. This would be, in other words, like if I said, today we're all going to give a speech, and so I'm just going to randomly pick from our class. Well, once I've chosen 10 people out of our class, there's a more likely chance that you're going to be chosen next, because I'm not going to make you do a speech twice. We've heard your speech, we're moving on. I'm infecting that independence idea. However, if I said, you know what, everybody in the whole school is going to give a speech today, and I've picked 10 people from the entire school. Okay, those 10 people are not influencing the overall population. It's not so big that you're worried that you're going to be next, because there's still enough people left that you're kind of still in the same population pool. That's what this is saying. It says you can use this binomial setting, which again, that's what we want to do, with a simple random sample, as long as you do not sample more than 10% of the population. So what I do, instead of doing, 1/10 of the population, I might not know the population. So what I do is I check the condition 10 times my sample, and it has to be reasonably smaller than the population. This is our condition for independence. And so this allows us to kind of fudge the idea when we don't have replacement, when we're taking a random sample from a population, instead of, we're drawing a card, putting it back. We're taking a marble out of a bag and putting it back. So let's look at this example. It says an airline trained 25 new first officers become captains, 15 of which are male and the other 10 are female. Only 8 captain positions are available, so a lottery will decide who will fill the positions. Chosen from the lottery were 5 female and 3 male. Some complained that the lottery was not fair. Explain why the probability that 5 females chosen would not be equal to this. Okay, so when we look at this, this is saying we have failed our independence idea. When we looked at bins, okay, we do meet this criteria. It is binomial because we either choose a female or we don't, but this is where we fail. Okay, this is not independent because choosing one female now affects the rest of the numbers. There's only 15 or 25 of them that are going to be chosen for these 8 positions. And so when we take one out, well, changing it from 25, now the denominator to choose the next one is 24. That's going to change our independence. So knowing one outcome does influence the next. Okay, which means that even though we have a set number of trials, we are only picking 8 positions, our success here isn't going to be the same every time. And so when we look at this, this is going to fail as well. Not consistent because not independent. And so when we look at our rule, it says, okay, maybe we can get away with this setting if we meet the 10% rule. And so this rule says, okay, if these fail, maybe we didn't take such a big enough sample that it's influencing it. So we would take 10 times our sample. So we're polling 8. And this is going to be less than the population, okay? So in this case, 80 is less than our entire population that we were choosing from is 25. Okay, this fails. So when our binomial setting failed, this is kind of our get out of jail free card. If it fails, this is not a binomial setting. We can't actually find this calculation. All right, so let's look at another one here. In this example, it says there's a certain cereal company that has put one of 5 different cards into each cereal box. Each card features a different driver: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. Suppose that the company wanted to print out 20,000 of each card so that there were 100,000 total boxes of cereal with a card inside. Show that this is approximately a binomial random variable. All right, so we're going to choose one person. And I guess if I look forward, we're going to look at Danica Patrick. So when I look at bins, okay, to see is this a binomial random variable, does it meet this setting, we could say it's Danica or not. So that makes it binomial. We have success or failure. And then this would fail, okay? This is without replacement. Once you win the card, it's not like they're going to go put that back into another box. Gross. Okay, so how do we fix this? This is our 10% condition. And so our 10% condition says, okay, take 10 times our sample. Okay, so now again, I'm looking kind of forward. I should have put this line above. But if I took 10 times 6, okay, is that going to be smaller than the entire population? Meaning, am I sampling small enough that taking 6 out isn't going to really change this number? So when we think about this, this is 60. Is that less than, we said there's 100,000 cards there. This is absolutely met. So taking 6 out of 100,000 really hasn't affected the independence. So we will proceed here with caution. And I like that phrase, proceed with caution. It seems a lot more dangerous than what we're doing in statistics. All right, so we're going to have a set number. Again, I'm pulling from this second piece here, and we have a set probability. Everyone has a card, and Danica is on 1 out of those 5 people. All right, so because we've met this condition, we didn't on the previous example. 25 was far too small. We were taking more than our fair share when we were looking at 8. Here we're taking 6 out of 100,000. Even though it's technically failing because it's without replacement, we proceed with this caution idea. So what's the probability that if we bought 6, what's the probability we get exactly 2 Danica Patrick cards? All right, so this is going to be exactly 2, so I'm going to use my binomial PDF because I want precisely 2. I have set number of trials of 6. I have a set probability of 1/5. Notice I'm labeling my calculator speak. And I have a set number of outcomes that I want. I'm looking for exactly 2. All right, so in my calculator, I'm going to go to second distribution. I'm going to pick, going up, binomial PDF for precisely 2. And I have 6, 1/5, and 2 trials. And so there is a 0.246. Probability of me picking 6 boxes at random and getting exactly 2 Danica Patrick cards. And technically we could change this to any of them. So we could change it to Tony Stewart, to Jimmy Johnson, to Jeff Gordon, to Dale Earnhardt, and it would be the same probability because each one of them is weighted equally. So if we had changed this to what's the probability of getting a Jeff Gordon card twice out of 6 random boxes, we would still have a 25% chance there. All right, so again, we're kind of cleaning up a couple of things that we did with binomials last time, still checking the setting, but now we have this extra idea about independence as well as this new calculator procedure that's a little bit faster. Okay, so the last one here says, suppose that a count X has a binomial distribution with n trials and success probability P, meaning it's binomial. When n is so large that n times P is greater than 10 and n times 1 minus P is greater than 10. All right, so this is what it's saying here. When our sample, our expected outcome for success is bigger than 10, and our expected outcome for failures is bigger than 10, then the distribution is approximately normal. So we are now able to change the shape of a distribution. We've never been able to do that before. And so this is a kind of big deal in statistics. It says, okay, once we have this binomial setting, if it is so big that we have more than 10 successes and more than 10 fails in our outcomes, expected outcomes, then we have an approximately normal distribution. We have an expected value here and a standard deviation for our normal distribution. Again, these are provided for us on our formula sheet. So when I pull up our formula sheet, it says if X has the binomial distribution with parameters here, so they give us the calculations, but they also give us the mean and standard deviation. If it has the binomial distribution, notice that it doesn't tell us the condition in order to get to that. We are going to have to memorize this rule that says we need at least 10 successes and at least 10 failures to make it approximately normal. All right, so here's our last example. It says attitudes toward shopping. It says a simple random sample of 2,500 U.S. adults were asked if they agree or disagree with the statement, I like buying new clothes, but shopping is oftentimes consuming and frustrating. Suppose that exactly 60% of all U.S. adults, of which there are about 2.35 million, would say that they agree, not 2.35, 235 million, good grief, would say they agree to the statement. Let X equal the number in the sample who agree. Show that X is approximately a binomial random variable. Okay, so this is going to be a Bin's idea. So binary, agree or disagree. Independent, okay, well, once they asked one, they really just moved on. They're not going to be asking that person again. So this fails. because they're not replacing the random sample into the population. So this is without replacement. So this would fail. However, we have our 10% rule that allows us to check. We're taking 10 times our sample of 2,500, and we're going to try to make sure that this is going to be less than our 235 million. Okay, so when we multiply by 10, we get 25,000. That is still considerably less than our 235 population. And so this is going to be proceed here. So end, we have a set number of trials. So it says we are doing 2,500. So that's in our sample. And we have a set probability for success. They're telling us that's 60%. So we can say our probability for that is 0.6. All right, so we have gotten through one here where it says, okay, we have failed independence, but we can proceed because we passed this 10% rule. So what about becoming approximately normal in this setting? This is a huge sample. So can we check to see if it's approximately normal? Here's how we check that. We're going to check two things. Is n times p bigger than 10? And is n times 1 minus p bigger than or equal to 10? All right, so we're going to plug in our information here. So we have n, which is our 2,500, times p. This is our expected outcome. And so when I multiply those, I get 1,500, which does meet this criteria. And then here I'm going to do n 2,500. 1 minus 0.6, making sure it's also bigger than or equal to 10. And I get 100 here. That doesn't seem right. Let me double check that. $2,500 times 0.4. I think it's bigger than that. There we go, 1,000. I was like, something's not adding up there. All right, so we have 1,000 here, which now makes sense looking at it. We have our 1,500 and our 1,000 here, so we expect 1,500 successes, we expect 1,000 fails. And so because these have both checked out, yes, this is approximately normal. Okay, this is an awesome thing. We have now taken something in a binomial setting, and now we've made it approximately normal because we've taken such a large sample. So now if we use the normal distribution to estimate the probability that 15, 20 or more of the sample agree, well, now I have approximately normal. So I can say this is a normal distribution with an expected outcome of 1,500 and a standard deviation. Okay, this is where I need to go back to my formula and calculate. My standard deviation is going to equal the square root of 2,500 times 0.6 times 0.4. Okay, so I'm going to do that on my calculator. So I have square root of 2,500, and then there's our probability for success, and there's our probability for failure. So putting that in, I get a standard deviation of 24.5. And now I'm looking at this distribution where I have an average here of 1,500. I have 15, 24.5, 15, 49, 15, 73.5. And so when we're looking at our distribution, 15, 20 or more. So now we're looking at this distribution. And so we can say this would be the probability that our observations are more than or equal to 15, 20. Well, now we have a normal distribution where we always do CDF. We'll take 15, 20 to infinity. And then we have our mean and standard deviation. So we took something that's binomial and have now changed it into the approximately normal distribution. So on my calculator, now I can go to my distribution menu, just like we've been doing for a long time here. And we can do our normal distribution. Second distribution, normal CDF, there at the top, and we have 15, 20. And then we have our really big infinity number, 1500 and 24.5. And we get a probability of about 20.7% here. And so as we're looking at this, we want to kind of consider like this idea of taking something and changing its shape. We've talked about random variables that you can't change the shape, even if we add, multiply, if we combine them. We said you can't change the shape. What changes the shape? If our distribution is large enough, successes and fails, then we can get to an approximately normal distribution. All right, let me know if you have any questions.